Good afternoon, everybody. Welcome to the Flowmaster educational webinar this afternoon on modeling two-phase hybrid thermal management systems. My name is Andrew Hintz, Application Engineer at Flowmaster USA. We'll be joined later on by Richard Hoyle, Principal Engineer from Align CAE, to discuss his use of Flowmaster for this specific type of modeling. For now, I'll be hosting the first half of today's event. Today's webinar is designed to educate engineers, both Flowmaster and non-Flowmaster users, on methods and manners in which Flowmaster can be used to model and analyze a modern hybrid cooling system, using both coolant flow and two-phase refrigerant flow. During the first half of the webinar, I will give a brief overview of the systems that Flowmaster can model, as well as a brief summary of the typical design challenges faced by engineers. I will then describe Flowmaster's capabilities and different methods as to how Flowmaster can be utilized to analyze a standard cooling and AC loop. We will conclude with Rich Hoyle from Align CAE presenting a synopsis of current design challenges as well as a discussion of how he incorporates Flowmaster in his analysis process, focused in on simulating the electric and hybrid vehicle thermal management systems. Flowmaster can be used to model many of the fluid systems found in a vehicle, including but not limited to the ambient airside flow, cooling systems, lubrication systems, AC, exhaust, and fuel systems. Today we'll be focusing on the cooling and AC systems particularly. Hybrid vehicles pose additional challenges to engineers when designing these types of systems. New thermal loads on the system mean new thermal management tactics. Components unique to electric and hybrid systems represent additional heat loads which need to be accounted for when sizing the overall thermal behavior of a given system. The battery, battery charger, and inverter temperatures, just to name a few, need to be monitored and regulated. For these components, the engineer has to make sure that the standard operating conditions are maintained within certain performance parameters so that the chance of failure is minimized. Of course, when a system is altered to accommodate these new thermal loads, the engineer must also be sure that the traditional components maintain their operating temperatures, flows, and pressure drops. This may require new sizing to achieve optimal performance and best utilize physical space available under the hood. We'll move first into exploring the graphic user interface of Flowmaster. Flowmaster is a 1D system simulator software designed to allow engineers to quickly find values for flow rates, pressure, and temperature throughout their fluid flow system. Flowmaster can be used whether the fluid being simulated is incompressible, compressible, or a two-phase refrigerant. Engineers may choose to simulate their model in an adiabatic scenario if pressure drops are the main focus of concern, or they may choose to simulate heat transfer to take into account the thermal behaviors. These simulations can then be run either steady state to test for a single scenario, or transient to test for any number of variants within the circuit. The Flowmaster interface itself utilizes Windows-based code, which employs familiar tools to aid engineers in efficiently modeling a circuit for analysis. An engineer using Flowmaster will start with the drag-and-drop interfacing, which enables them to easily lay out the circuit's configuration and then connect components in the order in which fluid flow passes through them. When modeling their circuit, an engineer will have the ability to use one-arm source components to simulate boundary conditions. This means that a closed loop is not always necessary in order to model and run a successful simulation. Smaller sections of a network can be modeled and studied in greater detail using the source components to model upstream and downstream conditions. The component catalogs, schematic workspace, and simulation data are laid out in such a way that the work done in Flowmaster flows from left to right. The user begins from the left side of the screen, constructs models in the middle of the screen, and ends by running the simulation and viewing results at the right side of the screen. Here we see the graphic user interface. The interface starts with the project view window on the left side of the screen, where projects and any associated networks are organized and can be selected. Component libraries are also held here, and engineers can choose the components and graphic performance data, including curves and surfaces, that they want to include in their network. The components are then selected and dragged onto the white space or network schematic, where they can be connected, and the network layout is then graphically represented. Finally, an engineer will end on the right side of the screen where the network view window is located. The network view window is where data for the components is entered and results from simulations can be viewed. The component library within the project view window contains over 200 built-in analytical models to choose from. The majority of these models use correlations from D.S. Miller's Internal Flow Systems textbook. These include different pipe models, which account for pressure drops in pipes of different geometries, fluid flow phenomenon, and composition. It also includes orifices, valves, pumps, heat exchangers, and reservoirs, just to name a handful. Other components include an AC-specific catalog, which contains components for the compressor, evaporator, condenser, thermal expansion valve, and receiver dryer. Flowmaster also contains components that can be used to implement control logic or custom algorithms into a network, as well as enable real-time result plotting. Besides the built-in components, Flowmaster also provides a way to create your own component with all the capabilities of a standard Flowmaster component. The interface can generate a code stub as a starting point, and from there you write your code in either C# or VB.NET. To manage all the data, Flowmaster provides you with a centralized SQL database. This database includes all of the built-in data, including curves, surfaces, equations, and supplied fluid properties. In it, you'll find default data for many different types of control valves, orifices, and different fluids, like glycol water mixtures, oils, water, and certain refrigerants. Here you can also create libraries of information you enter once and use for all of your models. For example, you can create a library of coolant pumps to try out in your cooling system. The database architecture is designed with collaboration in mind. The backbone is the SQL server, which means many users can connect to the same data storage location. Different permissions can further be set up to control who has access to changing models and data. Moving into the different types of analyses, there are a number of different options the engineer has. Oftentimes, the cooling system designer will start building a model by doing a series of steady-state analyses without the use of the heat transfer solver. The goal is to characterize the pressure drop of the cooling passageways and size of the pump. They would use fluid properties close to the expected operating condition of the system. Next, the designer may add in heat transfer. This way, the variations in fluid properties due to changing temperature could be considered, as well as frictional heating in the loss components. More importantly, different heat exchangers can be tried to see what would be the impact on top tank temperature. Here's where a lot of cooling system analyses end, though at times engineers will investigate transient behavior, especially when analyzing thermostat controls to check one thermostat versus another. With newer technologies such as electric pumps and valves, a lot more transient work needs to be done. As a result, when we start doing hybrid cooling systems, there will be more transient scenarios to consider. In addition to traditional cooling loops, in electric hybrid vehicles, we now see two-phase systems becoming more prominent in modeling the overall system. Flowmaster has the capability to model these two-phase AC systems in both steady state to size the system and transient to see how it behaves for a desired drive cycle. In Flowmaster, an engineer can also see the system interactions between the cooling system and the AC system. So what does all this analysis return? Every time you run an analysis, Flowmaster will provide results for pressures and flows throughout the system. In a heat transfer simulation, temperature and heat flow will be included in the reported results. When running a two-phase refrigerant simulation, results for quality and enthalpy will also be reported. And depending on the type of analysis and components used, you'll also get some component-specific results. A few examples of these include speed and torque for a pump, thermal effectiveness for a heat exchanger, position for valves and ports, and liquid level in reservoirs and accumulators. To the right, we see examples of steady-state results being reported in a list format and transient temperature results being displayed in a graphical format for selected components. Here we have a traditional example of an internal combustion engine cooling loop. The system starts at the water pump, which is used to provide a pressure rise to drive the system. From there, flow moves to the engine component where we have to supply a heat rejection into the coolant flow. Coolant then splits with one path going to the thermostat and the other to the heater core. The cabin heater component represents the thermal interaction between the airflow to the cabin and the coolant flow to the heater core. From there, coolant flow reticulates back to the water pump. Moving back to the thermostat represents a split in flow between the bypass and radiator based on temperature. For the bypass route, we use an orifice and piping to represent pressure losses as it reticulates back to the water pump. The other path goes to the radiator, which represents the heat exchange between the ambient airflow and the coolant. Here we will use an upstream and downstream source to simplify the ambient flow path. We also have a two-arm reservoir used to model the overflow container, and throughout the circuit we use various piping to represent the pressure losses through plumbing. In this webinar, we want to explore the interaction between that cooling loop and an AC circuit. AC components are different from other Flowmaster components in that they contain additional algorithms to solve for the complexity of two-phase refrigerant flow. AC components can predict hydrodynamic variables of interest at any point in the system, such as temperature, pressure, flow rate, and density, which are common to all components, but can also predict quality and enthalpy important to two-phase refrigerant behavior. The AC model can also be used to predict flow rates, temperatures, pressure, and humidity of the airflow into the vehicle cabin. Main system performance variables such as heat transfer rates and subcooling in the condenser, cooling capacity and superheat in the evaporator, compressor shaft power, and coefficients of performance are also predicted. And as a result of a successful simulation, the AC solver will plot out a pH diagram typical for evaluating AC cycle performance. The AC model can then be linked to other models to explore the interactions between the AC circuit and other underhood thermal systems. The air conditioning cycle starts at the compressor. The compressor compresses the refrigerant gas, increasing the refrigerant's pressure and temperature. This component acts like a pump in that it has an intake side and a discharge side. The intake draws in the refrigerant gas from the evaporator, compresses it, and passes it via the discharge side to the condenser. The compressor differs from a standard pump in that it is used in the AC network to enforce the conservation of refrigerant mass. An engineer can account for this by calculating and entering a charge mass for the entire system, or allowing Flowmaster to calculate the system charge mass by entering data for inlet pressure and either discharge pressure or condenser subcooling. The AC heat exchangers, consisting of the evaporator and condenser, calculate the transfer of heat between the air and the refrigerant in the circuit. The evaporator represents the cooling and dehumidifying of airflow to the cabin, and the condenser represents the cooling of the refrigerant gas to refrigerant liquid by the front's air side. Flowmaster has two methods by which these heat exchangers can be modeled. The first method involves a built-in tool called ASOP, which allows an engineer to size a heat exchanger against actual test data with minimal geometric data. The heat exchanger components that use ASOP require at least one set of actual test data or manufacturer's performance data. The ASOP tool sizes the heat exchangers in an isolated network from the full circuit and allows the user to open a new data window in which they can type in the valid data. When the test data is entered, the ASOP tool then runs a Flowmaster heat transfer steady-state simulation using a series of shape factors to adjust for pressure drop and heat transfer correlations. ASOP then reads the results, calculates a percent error between the results and the test data, then adjusts the shape factor and repeats the process until the percent errors fall below a designated value. The size heat exchanger can now be entered back into the AC circuit and run in a simulation of the full network. Here we see an example of the data form, which will be populated by the actual test data, and the shape factors, which are then evaluated to within a small % error of the test data. Advanced or geometric heat exchangers represent the second method by which heat exchangers can be simulated. In contrast to the empirical type heat exchangers we previously saw, advanced heat exchangers allow an engineer to use strictly geometric data to define their behavior. This becomes very useful when no test or manufacturer's data is available to use. The advanced heat exchangers use correlations based on CLAN code developed by P&Z Engineering. The advanced heat exchangers include a connectivity data wizard to configure complex tube arrangements, as demonstrated at the bottom of the slide, as well as data fields to take into account specific geometry of fins and louvers. Next, we're going to move into actually running simulations using Flowmaster. First, in designing any automotive system like the one we're discussing, we'll first consider the impact of efficient and accurate concept design. As we progress from concept design to detailed design, then testing and finally prototype, the scale of possible design changes diminishes. In contrast, a particular design change may rise in cost as we move down the design process. Thus, the demand for simulation increases. Up to now, I've discussed some of the ways a model can be constructed. In the next few slides, I'll give a brief insight into the multiple ways Flowmaster can be controlled and simulated to attain results. One such method is introducing controller logic into a network. Controllers allow an engineer to alter a specified data field for a component. This can be done using either a simple data table, master controllers which will declare global variables, gauges which draw results from other points within the network, an output transform that takes the input of a controller and passes it through a 2D or 3D transform before outputting the value, or a customized script can be written which can do a combination of any of the previously stated methods. Flowmaster can translate script written in C#, VB.NET, or JavaScript languages. These same controllers and gauges can be used to bridge Flowmaster to MATLAB Simulink for code simulation. Running Flowmaster through MATLAB and Simulink allows pre-existing MATLAB models to be able to send and receive data to and from Flowmaster, as well as allow for complex algorithms to be created in MATLAB, which can then be implemented into Flowmaster components. Through MATLAB and Simulink, Flowmaster models can then be linked with other software that can utilize a link to MATLAB. In response to this growing demand for better and more efficient means of producing results, Flowmaster includes as a standard capability the ability to run parametric studies. This built-in tool allows engineers to open an already tested and validated network, enter a selection of variable parameters, and then run a series of simulation which covers a desired range of data. This range may represent extreme cases or may simply be an attempt to find an optimal performance point. Once the range has been input, one click will then run the entire series of simulations and specific output values can then be analyzed. Using variable parameters makes it easy to track what data has been changed from simulation to simulation, as well as what results line up with what input variables. These input and output parameters are also easily exported to an XML file, which can be opened by most spreadsheet programs. The rows can also be simply copied and pasted into any spreadsheet. Now, we've seen this graphic before to illustrate the types of systems Flowmaster can simulate. From this point on, we're going to focus more on strictly the cooling and air-conditioned systems interactions. Commonly, the cooling loop and AC circuit are modeled individually as isolated networks. Results from one are then manually entered as input data for the other. This is a perfectly legitimate way of modeling systems. However, when altering certain aspects such as fan performance, ambient conditions, or compressor and pump speeds, it's not as obvious how the two networks may interact. One of the abilities unique to Flowmaster is the ability to model the two networks together so that they share airside paths. We can see from this graphic that the condenser and radiator share the ambient airside path as it passes from our upstream boundary condition through the condenser, then to the radiator and fan, followed by a downstream flow sink. The evaporator and heater core share the cabin airflow path in a similar manner. The air passes from an upstream pressure source through the evaporator to a three-way flap. Three-way flap then splits the flow between a direct route to the cabin and the heater core. After the heater core, the airflow moves into the cabin. In this model, we can make adjustments to any component and see how it will affect the system as a whole. At this time, we're going to explore how Flowmaster is integrated into the design and analysis process. And I'd like to introduce everybody to Mr. Richard Hoyle from Align CAE. Mr. Hoyle has over 10 years' experience in automotive powertrain cooling and HVAC CAE. He's currently the principal engineer for Align CAE, which specializes in 1D fluid flow CFD design and consulting.
Thanks very much, Andrew. Okay, I'd just like to start off by comparing what we'd see in a typical ICE vehicle as far as powertrain cooling and HVAC, and compare that to the next generation electric vehicles and hybrid vehicles that are coming down the pipe. With the ICE vehicle, we have to take care of engine cooling, cabin heating, transmission cooling, and often power steering cooling. With an EV and a hybrid vehicle, we still have to take care of these things. But we still have to take care of engine cooling, only for a hybrid, obviously. Cabin cooling is still a requirement. Cabin heating is actually a little bit more difficult because of the available waste heat in EVs and hybrids is not there like we see in an ICE vehicle. We sometimes have to also take care of transmission cooling, mostly just for hybrid vehicles, and power steering cooling sometimes. However, we now have another level of complexity from a thermal management point of view. We have electric motors that we need to cool. We have to cool inverters, which are driving the electric motors. We have to cool batteries. Sometimes we even have to look at heating batteries to maintain life. We have to sometimes cool a charger, depending on the current draw. We have transformers, which are going from high voltage DC to low voltage DC. And for hybrids, we have generators that often require cooling as well. So as you can see by this slide, on the left-hand side, we have a few components, and the techniques that have been used to simulate these have been pretty much, working for the last few years. We can still use similar techniques, however, we've just added a whole bunch more components that we need to take care of. So when we break those two into components, we have the ICE vehicle components here on the left-hand side. We have a cooling fan, which is, mechanical or electrical, a radiator, transmission cooler, power steering cooler, a cabin heater core, a cabin blower, cabin evaporator, cabin thermal expansion valve, condenser, the generic coolant plumbing, refrigerant plumbing. We typically, in an ICE vehicle, we see mechanical compressors driven by a belt connected to the engine. We have a mechanical thermostat, which is basically a fixed setting, and mechanical water pumps, which is driven by the engine. We have some similar components in the EVs, depending on whether they're a hybrid or an EV, but we have added complexity again. In some cases where if we have active cooling of a battery and active heating, we're going to have a battery evaporator, we'll have a battery heater, and sometimes we'll have a battery blower if it's an airside cooling system. Well, that could even be a pump if we've got a liquid cooling system for the battery. We have an electric compressor normally, as there's no engine for an EV. We have a lot of sensors that we're taking care of here. The typical ICE vehicle has sensors as well, but we've just added a lot of sensors now with EVs and hybrids. We're measuring things like temperature, all of these components. So we're measuring motor temperature now, inverter temperature, and DC-DC inverter temperatures and things like that. We're also concerned about things like humidity, particularly when it comes to battery thermal management. We have electric water pumps. Typically, we'll have more than one pump in the system now, whereas within an ICE vehicle, we may have had only a single pump. Coolant valves, which are often fully variable. So these aren't just like solenoid valves. These are actually fully variable valves to direct flow to different areas of the vehicle. We have PTC heaters or other types of heaters that are used to provide heat to the vehicle cabin, mostly for de-ice and cabin climate control. And we're also seeing the introduction of refrigerant shutoff valves to disperse refrigerant to different areas of the vehicle. Now, one of the really important things to understand about the EVs and the hybrids, the major components, is that these new components are often fully controllable via software, particularly the items such as the electric compressor, the battery blower, the electric water pumps, the coolant valves, the heaters, and the refrigerant shutoff valves are all controlled by an algorithm in the vehicle. These aren't fixed items, so we have a lot of control and a lot of different variables to play with, which is very important for when we're trying to balance energy consumption. This next slide just gives us a little bit of a snapshot of just how complex everything is getting. We talk about EV and ICE vehicle thermal loop. On the left-hand side is a snapshot of a combined AC and coolant loop for an ICE vehicle. It's quite a simple system, but it's typical to what's on the road today. On the right-hand side is a portion of what we're seeing in EVs and hybrids. This is about half of a typical circuit. So you can just sort of see, just by the pure number of components that we're adding, how much more complex it is. So why do we want to simulate thermal management in hybrids and EVs? The first thing, which is no different to what we'll be doing with an ICE vehicle, we want to make sure that we have the correct system sizing. So we want to optimize each component for cost, and we also want to optimize each component for mass. And this is what we've done, today in ICE vehicles. So we'll run a powertrain cooling simulation, make sure that we have the correctly sized radiator, cooling fan, we have the correct thermostat setting, etc., the correct size pump. What we're seeing now with hybrids and EVs, because of all the controls available to the individual components, is that algorithm development is becoming more and more important. And there's some questions that we've seen come up from our clients which are repeated. For energy consumption, we'd like to answer the question, is it more efficient to run a pump quicker or increase cooling fan speed? Because now we have the control over these. We have a brushless pump, for example, that we can increase speed, or we have a brushless DC fan that we can increase or decrease speed. So what's more efficient? Okay, so we have energy consumption on our minds all the time when we're developing control algorithms. Passenger comfort is another area of concern. Now that we've added additional cooling requirements in the form of batteries, how does that additional heat load on the AC system affect passenger comfort? And what do we need to do to make sure that passenger comfort is maintained? It's very important because now that if we add an additional evaporator into the system, does that steal refrigerant from the cabin? That's the question that we'd like to answer. NVH is another very important item that we're seeing in EVs and hybrids, mainly because of the noise or the low level of noise at idle, because you don't have that engine running in the background. Every little noise is heard in an electric vehicle. So questions such as, at idle, should we increase a fan or compressor RPM to maintain cooling performance? So the question here is as well, what's going to make more noise? We might want to compromise a little bit on energy consumption here for the sake of noise when we're in an idle condition. FMVSS requirements, questions like, will I have enough heat to satisfy federal de-ice requirements? Now that the internal combustion engine is eliminated from the vehicle, we no longer have a considerable amount of waste heat available. For an EV, it's even more of a challenge because there is no engine at all, so we need to add active heating in the form of things like PTC heaters. Battery life. Under what conditions will humidity management be needed? It's very important to keep the humidity levels down in lithium-ion batteries. and we can use evaporative air systems to do that. But how do we manage that? At what point do we need to switch on the battery evaporator to decrease humidity in the battery? Vehicle performance. How much energy is consumed by the thermal management system during a typical drive cycle? Obviously, with electric vehicles, range is a major selling point. So everything that we do in the vehicle typically focuses on mass, number one, and number two, energy consumption. So all of these questions, with simulation, we have the ability to gain answers and insight. That's just why we do the simulation for the hybrid and electric vehicles. So the next 6 slides basically break down the process that we go through when we're generating a simulation result for electric vehicles and hybrids. The first step, which is often the most time-consuming, involves the component data collection. And the sources for the data, they come from component suppliers. Sometimes we're using in-house simulation tools for particular components, CFD modeling as well. A lot of our clients require us to build full vehicle front-end CFD models as well as cabin CFD models. And what those models are used for is for generating front-end restriction curves, for example. So we can use those front-end restriction curves that are created by the CFD model, pull those into FlowMaster, and run an airside pressure drop study to determine what sort of airflow we're going to be getting through our condenser and radiator. Geometric heat exchanger, which Andrew touched on briefly previously, is another good way to get data, particularly if there is no data from suppliers or in-house simulation. And another important input into the simulation is simulation of the powertrain. And a lot of this simulation actually occurs in other tools such as MATLAB, where there's proprietary software that has been written to simulate an EV or hybrid powertrain. And this will give you information such as vehicle speed over time. It will also give you up a particular grade. It'll give you battery heat rejection, motor heat rejection, inverter heat rejection over a particular drive cycle. So they're all very important pieces of data that you need to be able to pull together to run a comprehensive EV/hybrid vehicle thermal simulation. The next step that they go through is to build our circuits. What we try and do is actually keep the coolant system and the AC system separate at this point in the development. We try and keep things very simple with key components only. So in this instance, what we try and do is, okay, we're not too concerned about valves and things like that. We can switch those manually. Refrigerant shutoff valves we don't typically have in the system. What we're trying to do here is to really just evaluate sizing for our components. We want to initially make sure that at an absolute worst case situation, we have available capacity to cool the various parts of the vehicle and also heat various parts of the vehicle. So for the sake of time, we want to keep things very simple here. We run in steady state. So this is just a single point in time. We might run 3 or 4 different points depending on the client's criteria, and to come up with a good idea about pump sizing, heat exchanger sizing, and fan sizing at this point. The next step, which is probably the most complex part of the process, is to actually combine the AC and coolant loops. And once again, Andrew did touch on this. Because of the complex nature and the interaction of all the components in a hybrid and EV thermal management system, it's very important to actually get a good understanding about how they interact with each other and how the whole system behaves over a drive cycle. And FlowMaster has a kind of a neat setup in that it has inbuilt standard drive cycles, US drive cycles, grades, etc., and some Euro and Japanese drive cycles as well. So that's already in FlowMaster. We also use that information, put that into a powertrain cooling simulation to extract our heat rejection curves over that same drive cycle. We use all this information, we pull it all together, we put it into FlowMaster, and we run a transient simulation over a drive cycle. Now, over this drive cycle, what we're varying is things like heat rejection from the motors, We're also varying front-end airflow because the vehicle speed is changing over time as well according to the grade and acceleration requirement of the vehicle. We're varying things like battery heat rejection. So over this drive cycle, we have a fixed scenario for all of our components to start with. And we basically get transient plots of things like evaporator discharge temperatures, compressor head pressures, also radiator top tank temperatures. They're the main things that we're really concerned about during these drive cycles. The other thing we try and take into consideration is the thermal mass of the components as well. So the motors and inverters themselves actually have quite a bit of thermal mass. So what we see is often a lot of heat soaking and thermal lag as the system gets up to temperature. That's all taken into consideration during the transient simulation. In a steady state simulation, those thermal masses don't have any effect because it's just a single point in time. After we combine our circuit and we run our initial transient analysis, what we'll do is look at iterating and optimizing the design based on the transient analysis result. And we will start by using the parametric study tool inside of FlowMaster. And one of the areas that we use a parametric study for is actually to run a typical charge determination cycle for refrigerant. So what we're doing here is iterating refrigerant charge in the system and evaluating compressor head pressure, evaporator discharge pressure, and condenser subcools over that cycle, just like one would run in a climatic wind tunnel when they're doing a charge determination. Because at some point you need to fix a charge in the system. Other areas that we look at is doing sensitivity analysis on things like pumps versus fan speed. And that was one of the items I spoke about previously was, is it better to increase the fan speed or the pump speed? And this parametric study gives us a good idea of what's more efficient because we can fix one variable and then vary another and get a full suite of results very quickly inside of FlowMaster. And we can post-process that data in Excel by creating charts and things like that, as well as some simple post-processing tools inside of FlowMaster. Once we've run our transient simulation and we've optimized our components, we look at algorithm development. And there's a couple ways to take care of this with FlowMaster. The first one is using FlowMaster controllers. And in this case, the algorithm itself is developed inside of FlowMaster. What the FlowMaster controller does, it takes inputs from regions of the systems in the form of a gauge. And a gauge can measure things, variables such as temperature, pressure, refrigerant quality, etc. Then what it does, you can write an algorithm that's embedded inside of the controller that interprets that data. And then that data then becomes an input to another component. So you can, based on, say, for example, head pressure, we can vary compressor speed or condenser fan speed based on this controller. So once we have these controls in place throughout the system, what we can do then is go back and rerun the transient simulation. So this gives us a good idea of actually how our software is going to behave when we're actually driving the vehicle down the road. Another way to do this, which is a little bit more complex but more powerful, is integrating controllers and gauges with MATLAB Simulink. This is currently done quite often for the development of automatic climate control systems, and this technology is being ported into control systems for EVs and hybrid vehicle thermal management. What the advantage of integrating in MATLAB and Simulink is, number one, it's a common user interface that is used by many electrical and software engineers in developing algorithms. So the logic can be put inside of MATLAB and Simulink, and that same logic can be used for actually programming the hardware. So that's the first reason. The second reason, which is very important, is that there's many other simulation tools and CAE tools out there that integrate with MATLAB and Simulink. For example, there's a large proportion of EV powertrain simulation tools already embedded in MATLAB or linking to MATLAB Simulink. So what this means is that you can start to create very complex simulation scenarios where we are running a transient powertrain cooling simulation in real time using our algorithm that we've embedded into MATLAB, driving FlowMaster, and having an organic algorithm that adjusts itself just like you would be seeing in the vehicle. The sixth step involves the algorithm optimization. Algorithm optimization is something that's typically done either in a climatic wind tunnel or out on the road. It's a very time-consuming activity. What we like to try and do is try to get a good idea of our calibration factors in our lookup tables before doing any vehicle testing. And there's tools out there such as Mode Frontier and EyeSight that are really powerful in multi-objective optimization. So what this allows us to do is to run our algorithm in Flowmaster, but this tool sits on top of all of that, and it will vary the lookup values that are inside of Flowmaster and our calibration. So we get a good idea of where our calibration needs to be before we actually start to physically test. And we create a Pareto front based on that study. So we're optimizing here for power consumption, noise vibration, harshness, comfort, battery life, and performance. This is, number 6 is something that's not in production yet. It's being developed, but it's a really exciting area in CAE, and we're really happy to present that.
Well, thank you very much, Rich.
Great.
Just to summarize, what we've covered so far is the new design challenges that engineers are facing when modeling electric and hybrid type vehicles. These challenges do present new and unique ways that engineers have to take a new look at modeling. Flowmaster has the capability to meet these additional demands in both cooling and AC systems of the vehicle. Whether it's taking on additional components in previous networks to account for additional thermal loads, modeling and analyzing interactions between networks, incorporating more robust controller logic, even using co-simulation to achieve the larger picture of the system's behaviors. We also saw, through Richard Hoyle, how Flowmaster is incorporated into this process. At this point, we've concluded the presentation part of the webinar.